and things like that. So hugely important field. And finally, protein folding and stability. Why is that there? That's the cow. And I'm following one of the advices I've picked up over the years about presenting. Say cow, see cow. So this is about mad cow disease and Alzheimer's and other diseases which are all related to the or affected by problems of protein folding. So that was my fourth example of functional properties that are associated to structure. And in all of these, electrostatic effects are determining physics. So I'm just going to give a brief, high-level idea of overview of some of the mathematical models that are involved. Just to give you like a map, some pointers of the type of equations that you sort of would need to understand, and then you have to go to a book and study them on your own time, because obviously on this limited time we can't explain or derive them one by one. I just want to give you a list. So first of all, the idea of, well, Coulomb's law, that the free energy of bringing two charges together in vacuum is proportional to the two charges divided by the distance. And this 332 right there is just a unit conversion in that equation so that you get the result in a common unit used in these calculations, kilocalories per mole, where the distance here would be measured in angstrom. So this would be the equation that you would use in this sort of standard units. Now, with some manipulations, you can get to the continuum representation of the electric field, represented as an integral equation over there, where rho represents the charge density. Again, we have some distance involved. The electric field is related to a scalar potential, and here is where our differential operators are coming in. Manipulation, again, of the previous ones leads to the equation. Do I have a pointer that I can you see this? Okay, the Poisson equation. Okay, a Poisson equation of electrostatics. Now, this Poisson equation, as the ones before, above in this presentation, are all valid in vacuum. But if we are looking at electrostatics in a medium, in a solid medium, then we have to add this dielectric constant that determines how the medium shields the charges from seeing each other in very simple terms. Now, so I'm adding little elements of complexity as I go down this slide, and the final one here is when, in addition to being in a medium, we have free ions in that medium. We have ions present, and this is the environment of biology. Most of the proteins are in water, or a solution of water and ions. This is the biological fluid where humans are 75% water, and every other living form is mostly water, and presence of ions there is what's going to determine the electrostatic interactions. So these are the equations we have to understand and deal with in this subject. Some of the difficulties, well, we've gone to a differential equation, right, representation. So it's a continuum approximation. And that is problematic, to say the least, at a molecular level, where perhaps the quantum effects are involved. And so one has to bear in mind that in this assumption of continuum, we could be making some smoothing effects or overestimations, underestimations, and so on. There's an assumption here involved, so that one has to keep in mind. Another difficulty in this representation is that we have assumed that there's a dielectric constant, that it's constant, and that's unclear when we're applying it to a heterogeneous media, like in biology. So the alternatives, of course, is to use microscopic models where we avoid the traps of these continuum approximations, but we are left with having to model at the atomic level every single interaction, with, of course, the computational difficulties that entails. So there is a hierarchy of models going from the microscopic there are some simplified microscopic models that I won't mention. You can find them in the literature. I will, as I said, give you some references, which approximate the effect of the heterogeneous media around the proteins by some sort of, I'll say, a lattice approximation or something like that. It's an intermediate approximation. And then there's the macroscopic, the continuum approximation. And that is where we're going to that is where we're working in my group, in the macroscopic approximation, the continuum approximation. So this is the model that is used, the Poisson-Boltzmann model, one of many, and there are detractors as well as faithful defenders. But let's keep an open mind. And in terms of discretization, there's, of course, the possibility of using differentially finite differences to discretize this and then calculate. And there are a number of very successful works out there using finite differences. There's some code, open source even code, to use finite difference approximations. But this means that we're going to have to construct a mesh. So imagine we have a very complex geometry, the geometry of a molecule, a macromolecule, involving perhaps thousands of atoms, and we're going to have to put this in a mesh to do a finite difference approximation. So that also could have some difficulties. A three-dimensional mesh involving complex geometries, as we know in computational fluid dynamics, is always a challenge. So in biology, it is as well. So treating the shape of the protein in detail, as I said, a difficulty. And again, we use macroscopic dielectric constants for both protein and solvent. Okay, so that's just the model. But instead of doing finite difference, there's another approach, which is the one we are using. And I will just give you this slide to give you an overview, and because I know there's a lot of people, a variety of people here, I didn't want to get into too many equations, and for those of you who want to go into more details, I'll give you references. The idea of the model is the following. So we have a Poisson-Boltzmann equation. We have an equation that is an elliptic operator, and we're going to be able to use some techniques for these types of partial differential equations, which are based on boundary representation by doing the following approximation. First, that cloud there actually represents a molecule, and we're going to imagine that inside the molecule we have one material with one dielectric constant, and outside we have another material, the water, the solvent, with another dielectric constant. In addition, there are point charges inside the molecule in the positions of the atoms. And in this approximation, the effect of the charges on the material can be represented by a distribution of charges on the surface. And basically, we have a Laplace equation a Laplace equation outside in the solvent, Poisson equation inside, and an integral equation on the boundary. An integral equation that when solved, is going to give us the charge distribution, which is equivalent to the effect of the full three-dimensional electrostatics problem. Okay, this is a boundary element representation. It's used in many applications in engineering, and there are many, books and everything. And there's a very good review paper that I can point you to. In particular of the boundary element method accelerated by the fast multiple method, which is what we use. Now, the boundary element method results, so it's an integral equation. It results in a dense matrix vector multiplication. This dense matrix vector multiplication can be accelerated using an algorithm called the fast multiple method. And this is what our contribution to the group effort is, the fast multiple method that we've been using for some time for other applications. We find we can, together with the acceleration of this algorithm in GPU, use it for this problem with great results in terms of performance. So I won't give you more details about the model, but I will give you some references for you, those of you who are interested in learning a little more. Let me just give you just 3-4 slides to finish this section of the presentation on what is sort of the vision for the future. Now, I'm not claiming that any of this is something we can do or many other groups. I mean, this is sort of the holy grail, the things that we're pointing to in the future that we want to do. And the point I want to make is that high throughput computing is going to be involved in the solution to enable those things in the future. Things like drug screening, in silico drug screening, mastering some of the degenerative diseases like Alzheimer's and mad cow disease as well. And personalized medicine. The only way that we're going to be able to produce these things for future technology is through computing, high throughput computing. Just to give you some examples. So the problem of in silico drug screening, the idea that we can simulate the combination of a small drug with a protein and observe the structure function correlation of that, see what happens, and simulate that thousands and thousands of times so that we can weed out inactive compounds, the ones that do nothing, and perhaps make a ranking of the most effective molecules for a certain functional change. To give you an example of what that entails in terms of computation, here's one. CERN used distributed computing a few years ago to simulate 300,000 potential drugs against avian flu. This took 2,000 computers working for 4 weeks, a total of 4 years of CPU time. So this just gives you an idea of the magnitude of the problem, just to study 300,000 potential drugs against one sickness. And there's hundreds of sicknesses that one would wish to develop drugs for. So this is the magnitude of the problem. And clearly, high throughput computing is going to be an enabling technology here. Another very hard problem is that of protein aggregation. This is the fact that proteins can sort of cluster together and form little sort of crumbs, okay? This is involved in some degenerative diseases like Parkinson's, where, of course, the formation of these aggregates is abnormal. And it's also involved in the production of drugs where the aggregation process is undesirable because it produces clumps that you don't like. The timescale of the conformational changes that is involved in this is in the order of minutes, which of course would be impossible to do with molecular dynamics alone. So we need some approximations. We need to look at the problem in a clever way to get some answers, perhaps within a certain degree of accuracy. Perhaps you can live with some degree of error, but so that you can sort of focus in on a parameter range of solution, where then you can perhaps use microscopic detail, molecular dynamics, to continue studying. So these tools need to be used in concert.
So, Lorena, One, two, three. Okay, Lorena, is the purpose of the study of protein aggregation an intervention, or it's at this point to study the nature of aggregation?
You asked me a question that is a little bit beyond, of course, what I would be comfortable answering in terms of my expertise, but I believe what I understand is that you want to study the propensity of certain proteins to aggregate, and the propensity of certain proteins to aggregate will give you understanding about these sicknesses, and that can be done by simulation. The dynamic simulation of the whole aggregation process would be just too great a problem, too great a challenge, I believe. But studying this functional feature of certain properties, the propensity to aggregate, through obtaining measures of, say, energy states and so on, is something that is feasible to think about. So but you can see how this could be a very, very challenging problem for simulation. It requires a huge amount of computing power. So to finish this topic, I just want to summarize